Welcome back, ladies and gentlemen. And now in this episode, we are going to talk about some architectures. Well, in the past, we have not taken the time to discuss different approaches and neural network architectures to solve this time series related trading classification problem. But in this case, we are going to dig in a little bit deeper. Not too deep, but I will show you at least two other ways of creating an architecture that is suitable for this problem. Well, in the last video, we have created this fully connected neural network, if you would say so, because the dense layer, as it is illustrated here, represents, in this case, 700 units that are fully connected, for example, to this 511 units from the next layer. That means you can multiply these, and these are a lot of parameters. And this is usually the first approach you can take to train a neural network, because it usually works out quite well. For images, for example, this is not suitable because you got millions of pixels, and if you use fully connected layers, there is a great amount of information to process, and there are several other ways to do this more efficiently. Okay, we have to do it again like we did it here, but let's go to architectures again and create another neural network. We call it DJI for Dow Jones Industrial. Again, we have to choose a label, like in this case LSTM for long short-term memory, and 703. You can name it however you want, but I do it this way so I know later on what I've done. Again, we have to cut out one of the shapes here because it's not an image, it's just a table with one line of data flowing in, like I type in the 700. We got 700 values for one example, but to use a long short-term memory network, we have to recreate the data set into its, I would say, original shape. Therefore, we use the so-called reshape node, right? There's a knife shaping the array. So what are we doing here? We have to click the minus again. And what you already know is we got 100 time steps of 7 features. I've shown this to you in the introduction video as well as in the training video. And 700 input values is now represented in 107. That means 100 time steps, and 7 features. So you got blocks of 7 features in throughout the distribution of time, right? This is the way the LSTM is able to process the data. Now we pull it, long short-term memory network, and hit it. I would say we just start over with 100 units, might be okay. Leave everything else as it is. The activation function as well as the recurrent activation. I don't have that much experience in changing that. As far as I remember, it did not help very well. So afterwards we have to use a so-called flatten node, because the output of this neural network is 100x100. And to use this any further, we have to multiply it out so that all these values are are in one shape, not in two shapes, right? This is 2-dimensional, and we need a 1-dimensional representation of that. So we flattened it out. Now I usually use a dropout layer, like in the other example. Let's choose a prime number again because I like it, 19. Okay, so that's it. And now we have to put in a dense node, for example. let's choose ELU again because it's training pretty fast. And yeah, let's say we got 10,000 here. Let's take something like 1,111. We use a layer normalization on that, and now, yeah, like maybe 311 ELU, and let's get down to 3 and softmax. Okay, make it beautiful. Okay, let's get over it again. We got 700 input values. We reshape it to 107. It's just a two-dimensional representation of this 700 values that are represented on the top here as one dimension. And then we feed it to the neural network, the so-called long short-term neural network, memory neural network. This was the state-of-the-art way of doing sequence modeling, also for languages and so on, before transformers came up, because transformers, they have been invented because long short-term memory networks, they can just be trained in a serial way, and that means they are pretty slow in training them. And yeah, transformers can be trained in parallel, so they come up with it, I think 2018. It was a team from Google, and yeah, you've heard about it because also ChatGPT and so on are trained on huge transformer networks. But this is much too complex, or too, yeah, you don't need this kind of complexity here for things we do. Okay, so now we got a LSTM, and we will also create another one. Let's call it DJI conv for convolutional 703, and create. And we start again as usual, minus 700. And now we have to do the same like we did with the LSTM. We have to reshape the data, because also the convolutional neural networks work with more than one dimension. That means we got like, let's have a look. Yeah, we got convolutional 1D, 2D, 3D. That means we need 1D. 1D uses two-dimensional inputs, so it's a little bit, yeah, misleading, the name, because usually convolutional 2D is used for images. You can see it in the small representations here. One dimension means like time series, so you got a two-dimensional input, and conv 2D uses a three-dimensional input for images, because images usually got three channels, like you got the height, the width, as well as the channel count for red, blue, and green channels, right? In this case, we got just two, a shape of two, so two different values, or two array, an array with two, with a shape of two, sorry, and we use this. So let's start with, yeah, a parallel approach. We will create three sequences of convolutional transformations or filter training with different filters. First of all, I will just put in three of these in one sequence, and will choose the ELU function for all of them to not forget it. Okay, I will do this first. Usually choose the same activation function for all the nodes. You can mix it up, but yeah, I've never investigated how we will influence the yeah, possible outcome then. You can check this out, no problem. So we combine them, and yeah, let's arrange them a little bit more nicely. Okay, structure is everything. So what do we have? We will start from the top left. The kernel size is telling you how many of the values are used for the padding. No, not really for the padding, but let's see if I can find something. Well, basically, the kernel tells you how many of the values are in focus for now. If you want to have more deeper insights on convolution and how it works out, there are a lot of videos on YouTube about image convolution. I can just drag and drop, for example, the two-dimensional convolution you see. This is a two-dimensional kernel, so therefore it's called 2D. And if you choose a three-dimensional one, you got it like this. Three-dimensional could be used for videos, for example, because besides the height, the width, and the channel count, you got also a time dimension. So we will change the values for all of the three sequences in the way of the kernel size. The amount of filters means, okay, imagine you got specific connections, like from one layer to another, and this is the amount of connections that occur, like in this case 200 filters. In the dense neural network you had connections from one unit to all of the other units of the next layer. In this case we don't do that. We want to save time, money, and computational power, so we just make up a specific amount of connections. In this space you would say filters, and usually to train or to create a convolutional neural network you got a fixed amount of kernel size and rise up with the filters the more you go deeper. Okay, strides is if you don't, in this case we go time step by time step. Okay, we use 7 values from the for example the first 7 values from the first 7 time steps, then we jump 1 time step ahead, and then we got the second, third until number 8, right, and jump 1 further. If we go like a stride of 2, you will see here it will change dramatically. It will be just half of the values it has been before. We will leave it to 1. 200 filters in all of the things, and here we go a little bit higher with the amount of kernel size, like 15, and here like let's say 25, for example. Okay, so that we got a different kernel size. Here we keep it the same. We have to do 50 again in the middle, 15 again, and 25 here, not 14, 25. And what we have to do now is we have to raise the amount of filters from one layer to another. That's the state-of-the-art procedure. If you want to learn more, just dig into this topic. I just want to show you how it's done here in our software and how to use this. And yeah, there are a lot of really good videos out there, like from 3 Blue, Ron Brown, and so on. He made great videos also about this topic. So now we have everything set up, and in the end we need something called global max pooling, for example, so that the output of all of these filters is like filtered again, because we would end up with 82 multiplied with 800, 58 multiplied with 800, and 28 multiplied with 800 values. That's a lot, and we don't want that because, as I already said, it's expensive computational power. We just pool out the maximum values out of that, so just 800 maximum filter values, and then we have to get everything back together with a concatenation node and do it like this. Okay, now there are 2400 values. We use again a dense layer, let's say a layer normalization, dense, dropout dense, combine it that way, make it a little bit nicer. Afterwards I will choose the amount of units too. Let's start here with again the elu function, and let's say 511, 300, or let's say 111 elu again, and here we got 3 values and the softmax function again. Let's save this. Okay, and now we are going to try this out. Let's go back to the project we have already created, and we will make up some additional pathways here in comparison, right, to make it easy to understand. We have to use another architecture. Maybe I should rearrange it a little bit that it's more clear to see what we use again or what we don't use again, because the data is the same for all the 3 models. What's different is the architectures. Here it's the LSTM, and let's start over with the LSTM. So to make it easier, so that you don't have to type in all the same stuff again, just click right and clone. Now you can take the node, right, and also the architecture. I have already chosen the LSTM architecture here, and we call it version 2. We could also call it version or LSTM, whatever. And let's choose data options. Okay, maybe in this case I will use another learning rate with 1 less 0, so that it might train faster and we don't need like for the epochs maybe. Let's start over. Let's see where this goes. Okay, so after like half an hour, or more like 1 hour of training, we reached a specific point where I would say let's stop training. We can now make a prediction too, but I would first try to train the other network too before we make the evaluation in the end. So let's copy or clone this training node again, link the data sets and use the convolutional architecture right here, link it. And what I would like to do here is, because it's a lot faster to train on a GPU I got here, as I already said, you can do this too, but therefore you will have to go here to your dashboard. I will save it. I can talk about that while it trains. I will go deeper into that on the deployment video. That's my how to say dashboard. You will have one too if you have registered, and here up there are the features you can buy for the software. We usually do business to business, B2B sector, so the prices are a little bit high for B2C customers. I will drop some discount in the next video on something that enables you for unlimited API requests. Just check that out then, but we won't get too deep into this right now. You can buy multi-GPU as well as single GPU. Then you will be able to train with the GPU, right? And as you can see here, if I choose this, let's check this out. You see the GPU memory is full and the training starts. It's a lot faster, especially for using convolution neural networks. Dense 2 LSTM, it's faster, yes, but not that much faster than CPU, like maybe 4 times faster. But using a convolution neural network is, in comparison, training from CPU comparison to GPU training is like 50 times faster. Okay, just to mention that. So we'll have a look how it is proceeding, and yeah, afterwards we'll make a prediction on that. So let's check this out. Okay, now the training of the convolution neural network is also done. Yeah, I've stopped it close to 50%, and I have also already done the predictions. One thing to mention here, the LSTM prediction will take like ages. So that means, like in this case, 2 or 3 hours, because in the prediction node each sample is predicted one by another, not in batches, right? So this might take a little time. What are we going to do now? So the accuracies for validation and training data set lie close to each other. Now let's have a look at the confusion matrices, if we can see or spot any big difference. You can see, for example, for the LSTM here, more hold traits are found correct, but also in comparison to the first one, less. It did more by traits or hold traits wrong as by traits, right? But yeah, to sum it up, in the end, it's a little bit better on the hold position. Also on the by position, you got like 8074. Here we got 8001. But it's less good in predicting the cell cases, if you want to see so here. And if we take the convolutional one, it's the network with the worst performance here. Fewer examples well traded or found in the not found, but not good predicted on the side of hold, right? And yeah, it's better on buying, if you would say so, and even worse on selling than the other two networks. Yeah, I would suggest you play around most of the time with fully connected ones. This is the easiest architecture to use, and for this kind of data, it's easy to use. So it's not a problem. So you don't have to make anything special to have good predictions. You just have to find at least good data or good labeled data. So you have to find the patterns you want to have, right? Okay, now we save this, and I will export this whole project and save it into a folder that is linked in the description. You will also find it on our website, as I told you before. And yeah, that's it so far. In the next video, I will show you how to deploy this model, right, to make backtests, to deploy it for trading, whatever you want to do, and how to do it. So, have a nice day.